Welcome back to the Agentic AI podcast. It is Thursday, February 12th, 2026.
Great to be here.
Today, we're tackling a subject that sits right at the intersection of physics and, well, the balance sheet.
It really does.
It's something that I think a lot of us in the enterprise automation space, we feel it every day, even if we can't quite put a finger on the technical root cause. We're calling it the hardware paradox.
It is, and I would argue it's the single most defining contradiction of our time in the tech sector.
And it is so frustrating. I mean, think about where we are right now. We have software that feels like magic. We have these agentic AI models that have grown from, millions to trillions of parameters in just a handful of years.
The software side is just exploding.
Exactly. We're talking about autonomous agents that can plan and reason and execute these really complex workflows. The software side of the house is ready for the big leagues.
But the house itself is kind of crumbling.
That's it. We are trying to run this futuristic 2026 software on hardware architecture concepts that, frankly, haven't fundamentally changed in decades.
The philosophy behind them is ancient.
It feels like trying to run a Formula One engine inside a horse-drawn carriage. You can hear the engine revving, but the wheels just aren't turning fast enough.
That's a very charitable analogy. It might be more like trying to run that Formula One engine inside a library where the data is stored, 3 miles away from the engine.
And that, right there, brings us to the villain of today's story.
The memory wall.
The memory wall.
It sounds ominous, and it should, because it is the single biggest bottleneck facing AI scaling today. It's not compute speed, it's not the algorithms, it's memory.
So our mission today is to unpack this wall. We're going to look at why our current chips, even the top-tier enterprise GPUs we're all fighting to get, are failing us. And then we're going to look at the breakthrough that's smashing that wall down. We're talking about 3D AI chips.
Specifically, how vertical stacking in these microchips is dismantling this whole bottleneck. We'll even dig into a specific prototype from Stanford that is really proving where the future of computing is headed.
And for everyone listening, whether you're an automation architect, a CIO, or just, someone obsessed with where enterprise AI is going, this matters. This isn't just about faster chips.
No, not at all. This is about the basic viability of your entire future AI strategy. It's about your energy costs, which are just spiraling out of control.
Right.
It's about shrinking training times from weeks down to days. And critically, for the agentic future we talk about, it's about being able to run these massive workloads privately, locally.
Okay, so let's get into it. Section 1, the bottleneck. Why exactly are our current chips slowing us down? I mean, I buy a new device every year, and it feels faster. Why is AI different?
Well, it really all comes down to the architecture. To understand the problem, you have to go back to 1995.
1995?
Yeah.
So we've known about this for over 30 years.
We have. The observation back then was simple. Processor speeds were improving by about 3x every 2 years. Moore's law in full effect.
Right.
But memory bandwidth, that was only improving by about 1.6x.
So the brain, the processor, is getting faster way quicker than its ability to recall information.
Precisely. Now, for normal software opening a spreadsheet, sending an email, that gap didn't matter all that much. The processor could wait a nanosecond here or there.
No big deal.
But in AI, that gap is fatal. We are seeing AI models grow their compute requirements by, get this, roughly 750x every 2 years.
750x. I can't even wrap my head around that number.
It is massive. And memory needs are growing by about 410x, so you have this huge divergence. The processor is just screaming for data, and the memory can't deliver it fast enough.
It's like having a Ferrari engine, but feeding it fuel through a coffee stirrer.
That's it. That's the problem.
Yeah.
And this is what's technically called the von Neumann flaw. Right?
That's the architectural root of the issue, yeah. Traditional 2D chips are built on the von Neumann architecture. It separates the compute unit, the brain that does the math, from the memory unit,
the storage.
And in a 2D chip, these two things are physically separated. They're neighbors on the silicon, but they are not in the same room.
Exactly. Let's go back to that library analogy because it's honestly the best way to visualize this.
Okay.
In a 2D chip, the books, your data, weights, parameters, are in a warehouse miles away from the readers, which are the processors. Every time the processor needs a fact, it has to drive all those miles, get the book, drive back, do the math, and then drive the result back.
That sounds exhausting just describing it.
And so inefficient.
Incredibly inefficient. And with AI, you aren't just fetching one book. You are fetching gigabytes, sometimes terabytes of data Constant.
Traffic on that road between the warehouse and the reader must be just gridlock.
It is total gridlock.
Yeah.
And that traffic has a real cost, a literal power cost. Data movement accounts for anywhere between 60 to 90% of the total power consumption in AI systems.
Hold on, let me just pause on that.
Yeah.
You're saying up to 90% of the energy my GPU is burning isn't even for doing math.
Nope.
It's just for moving data from point A to point B. That is the startling reality. Transferring a single byte of data across a memory bus takes about 1,000 times more energy than performing the actual math on that byte.
That is staggering. It's like paying $1,000 for shipping on a $1 item.
It's the perfect analogy, and the result of this is something we call dark silicon.
Dark silicon, it sounds like a sci-fi villain.
It might as well be. It's the villain of your ROI. It just refers to idle time.
Yeah.
You spend all this money on these high-end GPUs, and they often sit at only 20 to 30% utilization.
They're just waiting.
They are just idling, waiting for the data to arrive from memory. It's a waste of capital, a waste of time, and a massive waste of energy. If you're a CIO, you're paying for capacity you literally cannot use.
So the 2D plane, this urban sprawl of chips where everything is spread out, has hit a wall.
It has. We can't build the rows wide enough anymore.
Which brings us to the solution. If you can't build out,
You build up.
and that's the 3D AI chip. This is the paradigm shift, from urban sprawl to high rises.
That is the visualization. 3D AI chips stack layers of memory and compute vertically. So instead of memory being next to the processor, you put the memory directly on top of it.
Okay, so back to the library. This is like putting the bookshelf right on the scholar's desk.
Precisely. You connect them using what are called TSVs through silicon vias. Think of them like microscopic elevators that punch through the silicon layers.
So the data doesn't travel miles, it travels micrometers.
Right. We're talking about a massive reduction in the data path. And I want to highlight a specific breakthrough here from Stanford because just stacking chips has been a dream for a while, but it's incredibly hard to execute.
I was looking at the specs on this. They're using some pretty exotic materials, aren't they? It's not just silicon.
No, they are. They're using carbon nanotube transistors, or CNTs, and resistive RAM, or RRAM.
And why those? Why not just stack silicon on top of silicon?
It's all about heat. That's the physics constraint. Standard silicon manufacturing requires incredibly high temperatures, over 1,000 degrees Celsius.
Right.
So if you try to build a second layer of silicon on top of an existing one, the heat from making that second layer just melts the first one.
You burn down the first floor trying to build the second.
Exactly. But carbon nanotubes and RRAM, they can be fabricated at much lower temperatures, like 400 degrees or less. This allows them to build what is the densest 3D wiring ever achieved in a U.S. foundry.
Okay, let's talk numbers. Because this is where the aha moment really happens for anyone listening. The latency stats are wild.
The performance metrics are undeniable. In a standard 2D chip, your latency, the time to fetch data, is usually between 200 and 500 nanoseconds. With this 3D architecture, it drops to sub-100 nanoseconds.
So it's 5 times faster just to get the information. That's huge for inference for real-time applications.
At least. And then look at throughput. Early hardware tests on this prototype show an instant 4x performance gain. And simulations for taller stacks, building higher skyscrapers, they predict up to a 12x gain on Llama-derived tasks.
12 times the performance. That's a generational leap. If I'm running an agentic workflow that usually takes a minute to reason, suddenly it's taking 5 seconds.
Right. But the number that really blew my mind was the energy efficiency.
This goes back to that shipping cost analogy, I assume.
It does. Because the data barely has to move, the energy per bit drops from about 60 picojoules in 2D chips down to maybe 5 to 10 picojoules in 3D.
That's a 6 to 12 times improvement in efficiency.
It is. And when you apply that to the scale of global AI compute, you really start to see why this changes everything. This isn't just about faster gaming. It's about whether we can even afford to run these models at all.
Well, let's unpack that, section 3. Enterprise implications. Because if I'm an automation architect listening, I'm thinking, okay, cool tech, but how does this change my business, my P&L?
Well, the first and probably most urgent impact is sustainability and cost. We know data centers are projected to consume 8% of global electricity by 2030. That is an unsustainable trajectory.
It's a crisis waiting to happen. We're already seeing data centers struggling to get power grid approval.
We are, but 3D chips could cut the energy footprint of these large models by 3x. We could essentially have the projected global power draw from AI. For an enterprise, that's not just being green, it's a huge operating cost.
And it's about speed. If we solve that idle time problem, that dark silicon issue, What does that do to training times?
If you can get your compute utilization up from 30% to, say, 80 or 90%, then training runs that currently take weeks could be done in days.
That lowers the barrier to entry significantly. Right now, training a massive custom model is something only the tech giants can really afford to do on a regular basis.
Precisely. But if you cut the time and energy cost by that much, suddenly more enterprises can train their own custom models. You're not just renting an API from a provider, you are building your own brain, trained on your proprietary data.
Which brings us to the private AI angle. This is so crucial for our listeners' focus on agentic AI. You can't just upload your trade secrets to a public model.
This is where the hardware enables the whole private AI philosophy. The idea of private AI infrastructure, private AI appliances.
Right. To really unlock automation, I need an agent that knows my customers, my contracts, all my messy internal data.
And to do that safely, you need that high-performance inference to happen locally, on-premise. You can't rely on massive cloud clusters if you want total data control.
And 3D chips enable that kind of power in a small form factor.
Exactly. Because they're so dense and energy efficient, you can pack what used to be a server rack's worth of power into a much smaller appliance. A supercomputer in a pizza box, basically.
That changes the entire deployment model.
It means you can run these complex agentic workloads, real-time reasoning, retrieval, action, right there in your own building. Your sensitive data never leaves the premises.
So you could have an AI center of excellence running on hardware in your basement that delivers the same intelligence as a massive cloud model, but with zero privacy risk.
That is the absolute dream for the enterprise. Secure, powerful agents running on site, reacting instantly.
But I have to play the skeptic for a second. We've heard about revolutionary chips for years. So, Section 4, the roadmap. When can I actually buy this?
That is the inevitable reality check. We are likely, I'd say, 3 to 5 years away from a full, widespread enterprise adoption of this specific kind of monolithic 3D tech.
So 2029 to 2031, roughly.
Yeah.
Wait, if the prototype works, why not print millions?
2 big hurdles. First is heat. Now, we said 3D chips generate less heat per calculation, which is true. But because everything is stacked so densely, the heat you do generate gets trapped in the bottom layers.
The blanket effect.
Exactly. The top layers act as an insulator. Dissipating that heat from the middle of a silicon skyscraper is a huge physics challenge.
We can't just slap a bigger fan on it.
No. You need really advanced cooling, maybe even liquid cooling channels woven right through the stack, microfluidics.
That sounds complex.
Yeah.
And expensive.
It is. And the second hurdle is yield. Manufacturing a flat chip is hard enough. Manufacturing a stack where every single layer has to align perfectly at the nanometer scale, it's incredibly difficult. One bad layer can ruin the whole thing.
So high risk, high reward. What happens in the interim? We just wait for 2030.
No. We are already seeing hybrid approaches. You'll hear terms like 2.5D or hybrid bonding. It's where we stack memory next to the chip but connect them much more tightly.
Sort of a stepping stone.
Exactly. That will dominate the immediate future. And of course, the software needs to catch up too.
How so?
Well, our compilers, the software that tells the chip what to do, they're designed for flat chips. We need software that can think vertically, that knows how to optimize data flows up and down, not just left and right.
Okay, so we have a roadmap. It's not tomorrow, but it is coming.
It's inevitable. The physics demands it. We physically can't go much wider. We have to go up.
Let's bring this home then. We've gone from the memory wall to the 3D solution and what this all means for the enterprise.
We're moving from a world limited by how fast we can move data sideways to a world where data lives right on top of the compute. It's a structural shift.
And for the agentic AI enthusiast, the person trying to build the autonomous enterprise, the takeaway is really clear. We are all waiting for agents that can truly act autonomously.
Agents that can think and retrieve and execute in real time without costing a fortune or leaking sensitive data.
And this hardware is the key to unlocking that. This isn't just about faster chatbots. It's about enabling agents that can run continuously, reasoning and working in the background of your business 24/7.
And with an energy profile that is actually sustainable. That is the key.
It's the engine that makes the whole agentic economy possible.
That's right.
I want to leave our listeners with a thought here. We often talk about how AI isn't ready for certain tasks. We blame the models. We say, oh, it hallucinated, or it got stuck in a loop.
But we rarely look at the hardware constraint.
Exactly. If hardware constraints have been this silent leash holding back AI's true autonomy-limiting context, slowing down reasoning, what happens to the global economy when that leash is finally cut?
We might just find that the software was ready years ago.
It was just waiting for the silicon to catch up. A fascinating thought. That's it for this deep dive. We'll be tracking the development of these 3D architectures very closely. As always, thank you for listening.
Thanks, everyone.
We'll catch you on the next one.